Hey everybody, today we're going to talk about normal distributions, some of their properties, and something called a Z-score. Stay tuned. Okay, let's jump right into this. So normal distributions are really useful in statistics because they have certain properties that allow us to make inferences about them because all normal distributions have some things in common. Let me draw a normal distribution here. And here's my normal distribution. And I've represented the mean here. And there are some things that this normal distribution has in common with other normal distributions. If you've seen my other videos on normal distribution and standard deviations, one thing you'll know is that you need two pieces of data to describe a normal distribution. Other than that, normal distributions are identical. So you need to know where the mean is, and you also need to know the standard deviation. And this can result in something allowing us to do some things to compare across normal distributions, such as using a standard score. Right? A standard score is just a number that is easy to compare across two different distributions. So let's imagine the following scenario. Let's say we took a standardized test and we scored a 44 on the verbal and on the math portion we scored a 36. Okay? And let's say, for the sake of argument, that everybody else, the average for the verbal was 40, and the standard deviation was 4. Let's say the mean for the math test was 30, and the standard deviation was 3. So, looks like we scored a little bit above average for both of them. The question is, in which one did we do better? Well, if you just look at 44 versus 40 and 36 versus 30, it's kind of hard to tell, right? 44 is bigger than 36, so maybe we did better on the verbal. Right? But then we have to think, the mean was higher. Everybody did a little better on the verbal. So is 4 points above the mean the same as 6 points above the mean here? It's hard to tell. So what we can do is we can say, well, we know what the distribution looks like. Right? Can we compare across these two? In other words, can we kind of normalize or stretch the two distributions out so that they match up exactly and see where do we fall relative to everybody else? So that's what we're going to do. We're going to try to compare these. We're going to calculate a standard score, or what's called a Z-score. And the way a Z-score works is, instead of keeping the number of slices fixed, we're going to keep the width of the slices the same. Because think about it, in a normal distribution, there's no end here. This could theoretically go out forever. Since we're talking about a practical case where we're taking a test, presumably there's an upper limit. But in many things that we might measure in nature, like imagine we're counting the number of spines on a cactus. There might be a cactus that's just way over here off the charts. If that's the case, we don't know what the end points at the top and bottom might be. So instead of keeping the number of pieces constant and varying the size, we're going to keep the size constant and let the number of pieces vary because we don't know how many there are going to be. So how are we going to do that? Well, we're going to take our standard deviation. Right? That's going to be the value that we're going to use as a standard unit of measurement to calculate our z-score. So the z-score is going to be counting by standard deviations. Right? Okay, so let's draw a line down here of potential z-scores. The z-score is going to be how far away from the mean. Okay, so anything below here is going to be negative. Anything above here is going to be positive. If I scored exactly the mean, what would my z-score be? How far away are we from the mean? We are 0 away from the mean if we score the mean, right? So 0 is our starting point here. Now in this case, I said I have a mean of 40, right? And I scored a 44. How many standard deviations above the mean am I? Well, we can just count. 40 to 44 would be 1 standard deviation, right? So that would be here. And that's exactly where I am. So 1. So in this case, my z-score, I'm going to say z verbal, equals 1. Right? Because if this was 40 and this is 44, that's 1 standard deviation. What about the math score? And now we're talking about a mean of 30 and a standard deviation of 3. So 1 standard deviation would be 33. 2 standard deviations would be 36 above the mean, right? So 2. And that's our score. So we can stop counting there. So we've got, we are 1, 2 standard deviations above the mean. So our z math equals 2. Right? If we look at how well we did compared to the group for the verbal score, we did better than a good chunk of the people. But look at our math score. We did better, even better than that in math. So even though they have different means and different standard deviations, we can compare how we scored in the verbal and how we scored in the math. We're able to compare apples to oranges because we've standardized them. That's all a z-score is. Now, what if you talk to your friend and they say, oh, actually, I scored a 32 on that verbal test, right? Where would they be? Well, they would be, not this, if we count down 1 minus 1 standard deviation, that would be 40, minus 4 would be 36, minus another 4 would be 32. So they scored 2 standard deviations below the mean. Ooh, not very impressive score there. Okay, so we can say we scored a lot better in math than they did in the verbal, right? And so on and so forth. You can make all kinds of comparisons. So this is useful. Now that we know how to count a z-score, it's real easy when you have scores that are exactly a whole number standard deviations. But what if I had a verbal score? What if instead my verbal score was, instead of 44, what if it was 46? What do we do then, right? Well, remember, it was, Let's put our old numbers back here. So this is a mean of 40. And this would be 44. This would be 48, would be 2. So we know we're halfway in between here. Now, this one's easy enough. We can figure out that we would be at 46, which is exactly halfway in between these two. So that would, instead of a 1, that would be a 1.5. A Z verbal of 1.5. So, right? Because 40 plus 4 would give you the 1, and then an extra half again would get you to the 46, so we need 1.5. Okay. If you tried hard enough, you could find a number that was kind of unfriendly, right? So how do we deal with that situation? I'm going to give you a formula, and the formula is exactly what you've already done in your head, counting by standard deviations, but now we're going to use the formula just to sort of make it easier on ourselves. So the formula is this: Z equals the distance between your data point, X, and the mean, right? So X minus the mean divided by the standard deviation. Right? So now we can plug some numbers in here just to see how that works. So let's use our original number, which was, we scored a 44, and the average was 40, divided by our standard deviation, which is 4. That was our original verbal score, if you recall. So you get 44 minus 40 equals 4 over 4, which equals 1. Remember, we said that's what our original score was. Now let's erase this. Let's try the next one. Let's do our current verbal score, which we have at 46 minus 40 divided by 4. Right? Remember, all we're doing is counting up here. We're just using the formula to make it easier. So if we do this, 46 minus 40, that gives us a 6. It means we counted up 6. Now we need to divide by our standard deviation. 6 divided by 4 equals, it's the same as 3 over 2, which is 1.5. That's exactly what we said. Right? So what about one that's below the mean? And let's do a really weird negative one. Let's say our friend scored a 27 on the math. Right? So they scored a 27. Of course, the mean was 30. Oh, that one's too easy. Let me find a better one. If you follow that out, it's going to be 27. We know that's 1 below. So you don't have to actually need the formula really for that. Let's do 22. 22. So they scored a 22. And we need to subtract from that the 30, which is the average. Right? That's our X bar here. And we're going to divide by 3. So that's going to give us 22 minus 30 is going to be 8. Oh, this is a nasty number here, right? Divided by 3. So what is 8 divided by 3? Let's pull out a calculator real fast. 8 divided by 3. Okay, 2.67. Right? So we got that number, 2.67. There we go. So that's their z-score. And if we look at that, if we could plot it on here, so that'd be 1, 2. If we knew where 3 was, right? So this would be minus 3. Oh, I forgot. This is a negative number, right? So 22 minus 30, that gives you negative 8. So this is a negative, right? It's below the mean. So we go minus 2.67. So they would be right about here. Yeah, it's important to make sure you get your sign right when you're doing this, because that's going to tell you whether you're above the mean or below the mean. Now, a little common sense goes a long way. That's why I was able to catch my error here, because I can just simply look at the score and say, was I above the mean? Well, this number should be positive, right? In this case, it's below, so the number should be negative. So it's always good to get in a habit of going and checking your work and saying, does this number make sense? Right? So negative 0.67, right there, 2.67. Okay, so that's one cool thing about Z-scores that allows you to compare between two different normal distributions that have different means and different standard deviations. By using this formula, it allows you to standardize. Since you're dividing by the standard deviation, you're counting in standard deviations, and you can make comparisons across really different, dramatically different normal distributions. One of the cool things about normal distributions is that they have some properties that are consistent from distribution to distribution, and that allows us to know things that otherwise might be sort of elusive. So for example, how much of the data falls under the curve? Well, 100% of it, because that's what the curve represents. And so imagine that this is some kind of feature that you're trying to measure. Since I'm a psychologist, I'm going to think about it in terms of, let's say, this is the number of pieces of gum chewed in the general population, right? And so there are going to be a few people down here at the bottom who don't chew any gum ever, have never had gum before in their lives. And there's going to be some people way out here on the end that are just chewing gum like constantly, nonstop, and they chew gum while they're chewing gum. Most people are going to be kind of here in the middle, right? So as you go in these directions, they're going to be increasingly more rare. The further you go out this way and the further you go out this way. The most common is going to be somewhere here in the middle. Okay, so but 100% of the data fits under the curve. What if you are above this line, right? This is the mean line. If you're above that line, then that represents half of the curve, right? Because the curve is symmetrical. So half of the data is above the line, half the data is below. All right. One of the cool things we know about about these normal distributions is that the standard deviation gives this thing some properties. So, for example, we know that within one standard deviation of the data, roughly 34%, I'm rounding, 34% of the data is in this little region between the mean and one standard deviation. Another 34%, since they're symmetrical, is below. So that means in total, plus or minus one standard deviation gives you 68 and change % of the data. Likewise, when you get to 2 standard deviations, you get to about 95 and some change % of the data. The 95% line is actually, if you want to know, and this is kind of important for if you're going to do a something called a Z-test, 95% of the data lies in this line of between negative 1.96 and positive 1.96. That's the values that exactly 95% of the data fall between. So when you get out to 2, which is just a little bit more this way and a little bit more this way, you're at 95 point some change. Okay, so 95. And then once you get to 3 standard deviations out, you're at 99.7% of the data falls there. So only a tiny fraction, only a tiny percentage falls outside of 3 standard deviations. 3 standard deviations is pretty exceptional in either direction. Okay, so if you, and going back to our previous example, if you had a Z-score of 1, right, we could use that information to figure out your percentile, right? So if you have a Z-score of 1, we know that below the half, or below this average, is half of the data, plus another 34.1%, let's say. So 50 plus 34.1% would give you 84.1%. So if you have a Z-score of 1, you scored better than 84% of individuals. Right? Now that's pretty cool. We could find out how many people scored between your friend and yourself, right? What proportion scored between your friend and yourself? So if your friend was scored here and you scored here, we could figure out how many people are in this region in between. Right? So this allows us to do some really cool things with Z-scores. Now, how do you do that? Well, the easiest way is to pull up a table that has the Z-scores, and you can find out a Z-score of -4 is scoring better than only 0.003% of the sample. A Z-score of 0, not surprisingly, scores better than 50% of the sample. Right? If my friend scores a -1 and I score let's say I score a 2, they were better than the 15.87, and I was better than 97.72, I can subtract their percentile from my percentile and get a number. Let's see if I can actually do that. Let's see. So theirs was, mine was 97.72. 97, wow, come on. 97.72 minus 15, and what was it? 15.87. And that means 81.9%. So roughly 82% of individuals scored in between our scores. Right? So basically, any information we want to know, if we know the Z-score, we can convert each Z-score into percentages, and we can convert percentile scores back into Z-scores if we wanted to. Okay. Now this is what allows us to estimate. This is a spoiler alert for any future videos where we talk about statistical significance testing, because in significance testing you estimate a probability, and this property is what allows us to attach probability estimates to any given score. Right? So what's the probability I would score a 1.96? Well, that seems like a fairly rare event. Only 5% of individuals score better or worse than 1.96 or negative 1.96. Okay, That's too messy. I made it too messy, so I gotta get rid of that. Let's see if we can summarize what we've been talking about. So normal distributions are useful because they have properties that are consistent across normal distributions. If you standardize the normal distributions in terms of their standard deviation, right, count by standard deviations, you can create a standard score or a Z-score, which allows you to compare between different normal distributions with different means and different standard deviations. Finally, we can use that information to determine information about percentages and probabilities related to the normal distribution because since normal distributions are now standardized, they have properties that are consistent across these normal distributions, and that's what allows us to understand probabilities related to any normal distribution. It's a property that they tend to have. Okay, I hope that was a useful sort of introduction to Z-scores and how to use them and how to calculate one. If you want more videos like this, they're coming up. Be sure to like, subscribe, and I will see you next time.
It's Z distribution.